All right, next we are going to be starting chapter 7, which is titled Parametric Equations and Polar Coordinates. We're going to get to polar coordinates a little bit later in the chapter. Chapter 7, section 1 deals with parametric equations, and we're basically going to introduce the concept of what a parametric equation is, why it is important. We're also going to talk about how to convert parametric equations into an equation that has the form y equals f of x like we're used to. And then lastly, we're going to start to recognize some parametric equations as some basic curves, things like circles and lines and things that we are familiar with from regular functions of x or functions of y. So let's go ahead and first look at this example. There's a little figure here. And what this figure is, if you don't recognize the shape, it is an ellipse, right? And if you know anything about an ellipse, you may or may not have discussed this in pre-calculus, but ellipses have these 2 points in the center here that are called foci, or focus points. And they're important for drawing out an ellipse. And this particular ellipse is actually discussing the movement of the Earth's orbit around the sun over the course of 1 year. Now, if you know anything about an ellipse, or functions, I should say, if you know anything about functions, you would know that an ellipse or a circle is not a function. It doesn't pass the vertical line test, right? If we were to draw a vertical line through this curve, it intersects in more than one place, making it not a function. And a lot of the calculus that we've done so far, we've only dealt with functions, right? We've always dealt with things like y is a function of x, or x is a function of y. And we don't have this in this case, but there's still a lot of cases like this. There's a lot of examples where we want to be able to do calculus on graphs or curves that are not functions. So parametric equations give us a way to do that. Now, if you read through the little information here about this particular figure, figure 7.2, it says figure 7.2 depicts the Earth's orbit around the sun during 1 year. The point labeled F2 is one of the foci of the ellipse. The other focus point is occupied by the sun. If we superimpose the coordinate axis over the graph, we can assign ordered pairs to each point on the ellipse. So you can see that in figure 7.3. So now it's been redrawn. You have your x-axis and your y-axis, and the origin is right at the center of this ellipse. Then it says each x value on the graph is a value of the position as a function of time. So here you can see that. We have a point here, a point right here, and it has an x value and a y value. But notice each of those x and y values are functions of time. And that's where the parametric equations comes in. Each y value is also a value of the position as a function of time. Therefore, each point on the graph corresponds to a value of the Earth's position as a function of time. And so you can see this kind of playing out where January 1st is up here at the top, and at January 1st, or when t equals 1, this is the location of the Earth up at the on the y-axis. And as time increases, we move in the counterclockwise direction all the way around until we get all the way back to the starting point. And so October 1st, for example, is t equals 274. And so this is a scenario where we could use a parametric equation to write, or parametric equations, I should say, to write the equation for an ellipse, so we can use calculus to study different things about this scenario. So let's go ahead and keep moving down. It says most of the time equations of an ellipse have this form here. And I already talked about, normally we're used to seeing functions in this form, but we can't always do that. So let's look at an example of what I mean by that. Say we have the equation of a circle. You may or may not be familiar with the equation of a circle, but circles have the form x squared plus y squared is equal to r squared. So what if we wanted to try to solve for y or solve for x? Let's try to do that. So if we solve for x, for example, solve for x, we're going to get x squared is equal to r squared minus y squared. And then when we take the square root, we get x equals, remember, it's plus or minus the square root of r squared minus y. This is two separate equations. If you were to graph that, if you graph x equals plus or minus the square root, you have to enter two separate graphs to get that whole circle. In fact, if you enter the positive square root, you get the right side of the circle, and if you enter the negative square root, you get the negative half of the circle. So we actually need two equations, not one function, but two functions. If we tried to solve for y, we would have y squared. This is similar. We'd have y squared, and I just noticed I made a typo here. You probably noticed on the last side, the first when we solve for x, this should have been a y squared, and that means this should have been a y squared. Sorry about that. Okay, so again, solving for y, we have y squared equals r squared minus x squared, which means y is equal to, again, plus or minus the square root of r squared minus x squared. Again, it's two functions. The positive square root is the top half of the circle. That's when y's are positive, and the negative square root is the negative half of the circle. That's when y values are negative. So let's introduce then the idea of a parametric equation. Since we've now established that there are equations where we cannot solve for x or y, we need something new. And so what we generally take is we take a parameter t, it doesn't have to be t, but we take some new variable and we generate a function for x and a function for y that are both in terms of t. Again, t is called the parameter. And when we graph those parametric equations together, we get what's called a parametric curve. Now, it's still a two-dimensional curve, but it's defined by two separate functions, both functions of t, which a lot of times t is a function of time. So let's see how this works. So if we move on to example 2 talks about how to graph a parametrically defined curve. And the idea of this is really rather simple. So it gives you two functions, or two parametric equations. X of t equals t plus 2 and y of t equals 2t minus 3. And notice it says the values of t are only defined from -2 to 3. And so I have a table here, t values going from -2 to 3. And we could pick other values too, like -1.5 or 1.3. There's an infinite number of values in this interval, but we just picked out a few of them. And so when t is -2, what's x going to be? Well, remember, x is t plus 2. So when t is -2, that's, x of -2 is -2 plus 2 is 0. So x of -2 is 0. When we plug in -1, we get 1. When we plug in 0, we get 2. When we plug in 1, we get 3, and so on. So hopefully that idea makes sense, and we could do the same thing for y. y of t is equal to 2t minus 3. So when t is equal to -2, we get 2 times -2 is -4, minus 3 is -7. And we could continue in this fashion. Next one is -5, and -3, and -1, and +1, and +3. And so each one of these sets of parametric values for each t value generates a point, like we saw in the first the first graph, or I should say the first figure on the first page of the notes here. We saw each point corresponded to a point on our graph. So when t is equal to -2, that's going to make a point 0, -7. And when t equals -1, that makes a point 1, negative 5. So let's go ahead and plot this and see what we get. So I'm going to go ahead and draw my x and y coordinate axes. Here's y, and here's x. So our first point is 0, negative 7. Go ahead and put that on. So there's 0, negative 7. That, of course, is t equals negative 2. The next point is 1, negative 5. 1, negative 5, that's t equals negative 1. Then we have 2, negative 3. 2, negative 3. That is t equals 0. We have 3, negative 1. That's t equals 1. We have 4, 1 for t equals 2. And lastly, we have 5, 3. 5, 3 for t equals 3. And you can see that those points make a line. Now my graph was not perfect, but yes, this definitely forms a line. And one thing that we will, and actually I did not draw that line correctly because this line was only defined between t equals negative 2 and 3. So our line should start at t equals negative 2 and it should end at t equals negative 3. The other thing that we typically will put on a parametrically defined curve is we'll put little arrows to indicate how the curve is drawn out as t increases. So in this case, the arrows indicate that the line goes up to the right as t increases from t equals negative 2 to t equals 3. We could keep going. You can see in example B that you have two more parametrically defined curves. X equals cosine of t, y equals sine of t, and then in C you have two more curves. I'm going to go ahead and post the solutions for those since this is not really too difficult of a concept, but I want you to see how it works. You will see that in example B, that actually gives you a circle. This is going to be the graph of a circle, which should make kind of sense because notice x is defining cosine and y is defining sine. Well, that should remind you of the unit circle, right? And so even the ellipse that we talked about in the opening, that ellipse kind of has a similar form to the circle form. It's going to look a little bit something like our example in B. Then example C, it looks like x is something that's quadratic and y is something that's linear. Well, it turns out something like this is kind of parabolic in nature. So I'm going to let you go ahead and look at those two examples on your own, and we will have another video for this section, but that's going to do it for this one. Thank you.